My name is TraskCam,
I'm Cameron Barnhart.
and we're going to talk about BJT transistor characteristics and amplifiers.
So the main objective of the lab is to verify the IV characteristics of a BJT transistor, bias the BJT, and design a single-stage transistor amplifier.
We will sketch and design a common emitter amplifier with a gain of -10 and also with a quiescent current of 1 milliamp using a BJT.
We will use LT-Spice to design a schematic and test the bias points, test the gain, test the frequency response, and test how temperature will affect the circuit.
Finally, we will conduct our experiment by putting our design on a breadboard and testing to find our results.
Alright, so this is the theoretical side. We have our BJT transistor circuit all set up. We have VCC of 15 volts, an AC source of 1 volt peak to peak, and now we're going to calculate what each value for our resistors and capacitors should be.
So our objectives are, we want a gain of -10 volts, and we also want a quiescent collector current of 1 milliamp.
So what we're going to do first is calculate the RE. Since we want a quiescent collector current of 1 milliamp, we want this to be 0.5 milliamps. This is 1 volt, and that stays the same here. So we're going to have 1 volt over 0.5 milliamps, and that equals 2K ohms. So we can put 2K ohms right here. All right, so now to solve for R2. We know that R2 and R1 in parallel has to be less than the base impedance. And the base impedance is equal to RE, so this is equal to 2 kilo ohms times beta. And beta, we assume, equals 100. So since this has to be much less than this, 2 kilo ohms times 100, we're going to take 10 as a safe root. So we're going to do 2 kilo ohms times 10, and that equals 20 kilo ohms. And that's going to be our R2 value.
Alright, so now we're going to solve for R1. So we know that our input voltage is 1 volt, and for our base voltage, it's going to be plus 0.7 of our input voltage, so that's going to give us a base voltage of 1.7. Now our R1 value needs to be about 220 kilo ohms, and that's in order to satisfy. We're going to solve for RC, and we know that these two resistors control the amount of gain. So to solve for RC, we're going to use the gain equation, and that's gain equals negative RC over RE. And we know that our gain is -10, and that's going to cancel with this negative. And we know that our RE value is 2 kilo ohms. So these are C. Now to solve for this, we're going to bring the RE over to our gain, and that's going to be 20 kilo ohms equals RC. That's how we solve for RC. Okay. So for solving for C1, we use the cutoff frequency equation, and that is just 1 over 2 pi times 50 hertz times R1 in parallel with R2 in parallel with the base impedance, and that's equal to beta times RE prime plus RE parallel with RE. And that's going to equal 0.33 microfarad. Now for solving for C2, we just use the cutoff frequency equation, and that is 1 over 2 pi times 50 hertz, and then we look at our 20 kilo ohm resistor, and solving for that, that equals 0.15 microfarad.
So now, to maximize our gain, we're going to add in a resistor here, RG. And An equation that we can use to find RG is A equals RC over RE prime plus RG. We know RC is 20K. We don't know RE prime. And to solve for RE prime, you have 25 millivolts over 0.5 milliamps, which is our current, and that equals 50 ohms. So now we can solve, since we know the gain, we know RC, we know RE prime, we can solve for RG. So similarly for C3, we're going to solve it using the same equation, 1 over 2 pi times 50 times the resistance that we see here going into the capacitor, which is going to be 200 ohms. And that's going to equal about 22 microfarads. Alright, so now we have our circuit fully designed. And now we're going to start calculating what our value should be. So first we're going to find the DC bias points, which means all our capacitors are going to be open, which means they don't affect our calculations at all. First we're going to find the V base, and we know that the V base is 0.707 higher, so it's going to be about 1.7 volts.
So now to solve for the voltage across this resistor, we know that this is 0.5 milliamps and this is 1 volt, and we also know that this is 0.5 milliamps, and 0.5 milliamps times 20 kilo ohms will give us 10 volts.
Alright, so here we have our emitter part of our transistor, and we're going to look at what a potentiometer could possibly do to the circuit. So we have our RE potentiometer and our capacitor here. What the potentiometer does is it changes the resistance, and it's in parallel with RE. So if we make this 1 ohm, these two in parallel is going to be 1 ohm or less, meaning that our gain is going to be huge. If this thing's something like 20K, our gain is going to be huge. If we make this, but we can also make this really big to make our gain smaller if we want, and we can change the gain. That's what that's going to do.
Here we have our completed common emitter amplifier, and we have our DC source here, and we're going to measure our bias points. We're going to start at the base, where we get close to 8 volts. Then we're going to go to our collector. We get 15 volts. Now for our emitter, where we get 6.8. Okay, again we have our common emitter completed, and we're going to measure the quiescent current across our bias points. We're going to start at the base, and we find that we have a 0.3 milliamps. Then we're going to go to our collector, where we find that we have, again, just over 0.3 milliamps. And then for our emitter, we find that we have a current of right around 0.4 milliamps.
So this is close to the 1 milliamp quiescent current that we were looking for.
We had previously gotten all of our AC values in our experimental lab, but this is going over our graphs that we got in the lab. And this is our emitter voltage. It's a lot lower than we thought we were going to get at 280 millivolts. This is our input voltage of 1. And this is our output voltage. We were expecting 10, but got 8.96 volts. We're very happy with that, as it's very close.
So here's our schematic. We have a AC source coming in, then we have our DC sources up here. It's our base, collector, emitter, and all our resistors and capacitors. You can see the value. So the first thing we're going to do is a DC analysis, just a .op. I'm going to run it, and as you can see, our base voltage is 1.22, collector is 9, and our emitter is 0.6. So now we're going to run AC, click up here, turn for 10 milliseconds. We're going to run an AC analysis on that. So first going to do it here. So input, see it's 500 millivolts. Now at the base, see it's the same waveform but just higher up. Collector, it's a slightly smaller waveform, and then the collector have about 10 volts. So now what we're going to do is look at the cutoff frequency versus the gain, and this is going to be a frequency in which the capacitor is going to act as open, and it's going to be a frequency where it's going to act as short. So we're going to see what frequencies in which it works. We're going to dial AC deck 1000 to 100 meg, run it, and see here that at this is when it's at 20 dB, which means it's working, and when it's not, means it's not working. So at about 50 hertz or so is when it's working, and then to about a megahertz is when it'll work. That's the pass band. Alright, so now we're going to do a parameter sweep of this R load right here. It's currently at 10 megohms, and you can see the peak voltage is just over 13.5. We're just going to see how low it can go before we have current saturation and we don't get the amount of voltage we want. So we're going to try 1 meg. Run. And see it went down a little bit, but pretty minuscule. So 1 meg is acceptable. Let's try 500K. Just went down a little bit more, so 500K will probably work, but you're just going to get a little bit less. And then, oops. Let's try 100K. About the same. If you look and see, try like 100 ohms. See, we start getting really weird data, so let's try 10K. We're getting a lot of loss there. Still a lot of loss at 50K. I think it's going to be about 100K. That's what we want. Yeah, and that's just a little bit. It was at 13.5, so 100K, maybe a little bit more if we want a deal of data. 200K. Yeah, so 200K is the least you want to go on that resistor. I'll look at the temperature using the step temperature. We're looking at from 0 to 80 degrees Celsius on the emitter and collector nodes. Currently it's not letting me run it, but fortunately I have pictures. So here is the collector, and as you can see, as the temperature goes up, the voltage is going down by over a volt, so it's pretty significant. Then here we have the emitter, and it also goes up by over a volt rather than down. So yeah, the temperature is very important to these circuits. Alright, so here's our results. We have our DC bias points, base, emitter, collector, theoretical, LT spice, and experimental. Our theoretical and LT spice looked pretty good. I was really happy with how the LT spice came out, but our experimental values weren't even close for the DC bias points. But we asked several professors here at OIT, and they said that our circuit was working right. Just this is a hard thing to measure. So we went with these results. For the gain, for theoretical, 10 volts, that's what we designed the whole circuit for. CAD is 9.8, it's really close, it just has a little more real world stuff in CAD, so that's why it's not exactly 10. Experimental, we got 34 because Our output looked really good. Our output was like 9.8, but our input was 0.28 on the emitter, so that made the gain just huge when you divided those. So overall, our theoretical and CAD looked really good, but because this was such a tough circuit with transistors and it's easy to short circuit them using the probes and stuff, we weren't able to get great experimental value, but our circuit was working correctly.
In this project, we learned what a BJT is and that it has a base, collector, and emitter. For this circuit, we had a -10 gain, and we also learned how to calculate the different components of the base, collector, and emitter, whether it being current or voltage. And we also learned how to theoretically calculate the resistors and capacitors for the circuit. We used LT-Spice, and we feel more confident in our ability to design and utilize the different capabilities that LT-Spice has to offer for the circuit. All in all, our experimental values were pretty good. What we thought we were going to get and what we actually got, those values were a little skewed, but our circuit ran very well, and we're happy with how everything turned out.
Thank you, and good night.